Hello everyone and welcome to our webinar on Orca3D Marine CFD. The first thing we're going to do today is to start a live CFD simulation, which we will revisit later in the hour to show some actual results. So you're looking at the Simerics CFD software, and we just hit the start button. Okay, now that that's running, I'd like to introduce the panel that we have here today. First, I'm Bruce Hayes, one of the naval architects on the Orca3D development team. We also have Larry Liebman, a naval architect and the lead Orca3D developer, and Larry will be the main presenter today. Our colleague, Dr. Peter Bandick, is joining us as a panelist, and Peter is a naval architect and software developer with a specialty in hydrodynamics. We also have a couple of folks from Simerics in Bellevue, Washington. Simerics is the company behind Simerics MP, the CFD code that we have integrated with Orca3D. First is Dr. Cheng-Jae Wang, one of their developers, and we also have Rich Moore, their Vice President for Business Development. For those of you who may not be familiar with the GoToWebinar interface, you can click on the orange arrow to minimize the controls so that you can see more of the screen, and of course you can click it again to maximize the control. And if you have questions during the webinar for our panelists, you can type those into the question box, and we'll try to answer those as the webinar goes on, and we'll also do some questions and answers at the end if we have time, and otherwise we'll summarize the questions and answers in an email which we'll send out to all attendees after the webinar. Now I'm going to turn it over to Rich Moore, who wants to say a few words, and then Larry will begin the presentation. Rich?
Thank you, Bruce. On behalf of Simerics and Orca, we welcome all of you to today's webinar. You know, if you had to ask me what's the headline for this webinar, I would say the headline for today is Naval Architects Can Now Use CFD. You don't have to be an analyst to use CFD and Orca3D Marine CFD. Usable CFD has two parts. One, and most important, is the usable software that you'll see demoed today, and two, affordable pricing that we'll talk about later in the webinar. By combining Simerics CFD templates with Orca3D templates, we uniquely created Orca3D Marine CFD to enable naval architects to finally use CFD as they perform their designs. With that, I will now turn it over to Larry, and he will review the agenda and explain this powerful and strategic combo to all of you. Larry?
Thank you very much, Rich, for providing that background information, and welcome everyone to the Orca3D Marine CFD webinar. During the webinar, we're going to cover the items that you see here listed in our agenda. We generally expect the webinar to last about an hour, and it is being recorded in case there's something you'd like to review later or show to a colleague. So first, to put Orca CFD in context, we'll review why there's a need for computational fluid dynamics in the toolbox of today's naval architect. We'll then go on to show you how Orca3D Marine CFD meets that need and how the integration between Rhino, Orca, and Simerics works together seamlessly. Of course, performing high-fidelity analysis with CFD is only useful if you can trust the results. So Dr. Cheng-Jae Wang from Simerics has conducted a number of benchmark runs using a wide range of hull form types, and he'll go over and discuss the results of those benchmark studies. Next, we'll move on to a live demonstration of the Orca3D Marine CFD software so that you can see how easy it really is for the non-analyst to set up and run a CFD simulation. Finally, we'll wrap up the webinar with a discussion of product pricing, and if time permits, some questions and answers. So with that, we'll get started with our first item in our agenda, which is why do we need CFD? So why does someone designing a new boat or modifying an existing boat need CFD in the first place? Well, for many years we've been predicting hydrodynamic performance of our designs using a combination of our own experience, rules of thumb, and empirical prediction methodologies. In fact, Orca3D includes two semi-empirical drag estimation methods, one for planing hulls using the well-known Savitsky approach, and another one for displacement hulls using the Holtrip and Menon regression-based approach. Both of these methods are pretty reliable and quite useful actually for early stage design when you're deciding upon the gross proportions of your vessel. However, almost invariably, when you're creating a new design, you'll end up with features in the design whose effects are not well captured in the empirical method. For example, stepped planing hulls are very commonly seen today, and propeller tunnels are often found on inboard powered vessels that operate in shallow waters. And oftentimes we see the empirical methods don't capture these details. We frequently receive questions from the Orca users on how do I evaluate the impacts of design features like these. In addition, multi-hull designs are becoming popular in many segments of the industry. And while there are some empirical methods available for multi-hulls, the applicability of those methods becomes more limited as the design characteristics of the new multi-hull designs depart from the data on which the empirical methods are based. So this is where Orca3D Marine CFD comes into play. So our solution is Orca3D Marine CFD. A traditional solution to these issues has been to use model tests, scale model tests to assess performance. However, this isn't really a practical approach for many small boat designers and even has its limitations for larger commercial designs where you may want to look at a great deal of a wide range of alternatives for your hull forms, and that's not necessarily practical for a model scale test. A more contemporary solution to these issues can be found using computational fluid dynamics, which applies a first principles approach to analyze the fluid flow that is virtually independent of the geometry that you're analyzing. Specifically, Orca3D Marine CFD allows the naval architect or small boat designer who is not a specialist in CFD analyses to avoid or minimize the expense and time associated with model and full-scale test programs, to evaluate the effects of specific unique design features. So here you see a hull with tunnels and shafts and struts and a wake study that was performed using CFD. Orca Marine CFD also allows you to perform high fidelity design evaluation in earlier stages of design when decisions tend to have the largest impact. Traditionally, CFD analysis might be applied late in the design phase, but moving it to an earlier stage can be very effective. And lastly, and perhaps most importantly, Orca Marine CFD allows the designer to discover and avoid potentially costly design flaws before you go ahead and build the design. That's what, obviously, when you want to discover design issues. So what is Orca Marine CFD? Well, Orca Marine CFD is the integration between the Orca3D Marine plugin for Rhino with the CFD application for Simerics, or from Simerics. Many of you who are attending this webinar already use Orca3D, or if not, maybe are at least familiar with Orca, which adds marine-specific design and analysis functionality to the general purpose Rhino modeling tool. Orca CFD adds functionality to transfer much of the design information that you already have in your Rhino model over to Simerics for CFD analysis. One of the primary objectives in implementing this CFD integration was to follow the same philosophy as the rest of Orca3D by making it easy to use. For those of you who may not be familiar with Simerics, Simerics MP is a full-featured, multi-purpose brand CFD tool. As integrated with Orca3D, it includes those modules which are commonly needed for the analysis of marine problems, including a general fluid flow module, a multi-phase flow module using the volume of fluid-free surface, a turbulence module, and dynamics. Simerics MP offers several advantages over other CFD tools, including a very fast and robust solver, an automated mesh generation capability to facilitate fast and easy generation of high-quality grids, and a domain-specific template architecture. Rich had mentioned the template capabilities within Simerics, and this template capability is in large part what allows Orca3D to integrate so seamlessly with Simerics MP. Okay, so what can I do with Orca3D Marine CFD? There's a number of different types of analyses that you can perform. You can analyze both displacement and planing hulls, so we're not limited to one type of hull. You can generate resistance analyses as well as self-propelled analyses. And both monohulls and multi-hulls can be studied. So in this visualization you see here, we were performing an analysis on a catamaran looking at the effect of hull separation. You can also perform heave and pitch predictions. So in the lower right you see a planing hull that is starting from 0 speed and coming up to design speed, and you can see the spray route and how the heave and pitch of the vessel is changing. And we also allow you to analyze streamlines and flow around appendages and side forces and moments for models that have asymmetry. For example, a sailboat hull with appendages at a yaw and heel angle is shown in the bottom image. And finally, as Chen Jie will show you later in his presentation, you can even study porpoising instabilities of planing hooks. Okay, so how does Orca Marine CFD work? Let's talk a little bit about the process of using Orca CFD. It really starts with Rhino and Orca, which, as I said earlier, many of you are probably already using and have in your tool set. So you use your normal workflow, creating designs in Rhino using the native built-in Rhino modeling capabilities, together with the marine-specific design and analysis tools that Orca has, such as hydrostatics and stability calculations. Once this design is ready for CFD analysis, Orca CFD allows you to seamlessly transfer design information over to Simerics MP for post-processing. Here you see a list of the information that is transferred from Orca and Rhino over to Simerics. This includes the mesh geometry. Of course, the geometry is probably the most important part, the mass and fluid properties of the model, the static equilibrium attitude in order to initialize the simulation. We also take account of whatever unit system you're working in and whatever model orientation you've defined in Orca3D. If you're running a self-propelled simulation, propulsor information will also be generated in the data transfer. And finally, there's some Simerics-specific analysis information, such as whether your model represents a planing hull or a displacement hull has to be defined. Once in Simerics, the model is all set up and ready to run. Really, all that's left to do is to start the simulation and start viewing your results. So now that you have a little bit of an idea of how Orca3D Marine CFD works, I'm going to pass control over to Dr. Chen-Jie Wang over at Simerics in order to allow him to talk about how he performed his benchmark studies and what he's learned and observed from the benchmarks. Chen-Jie?
Hi, Larry. Thank you very much for the introduction. And thank you, guys. You probably already know how we integrate with Orca3D. And before our live demo, I just want to show you how accurate and how you can get the confidence from our numerical simulation. And I'm going to talk about a couple of these benchmark problems. The first one is the planing hull. It's a very simple design from Fismer, and this experiment was done in 1969. It's called Fismer hull. And it has a large variety in the experiment series. It has different design with the triangle. The experiment was a different displacement and a different center of gravity position. And here is one example of our comparison with the resistance, sinkage, and trim. As you see, with a different velocity ratio, we successfully captured the increased drag and also a sharp turn in the trim angle. And just want to assure you that we have a lot of these kind of agreements, and I'm just showing you one example of that. So, and also this is how how the free surface looks like. As you see, this is a very simple hull, but it's trimmed at a pretty large angle. As you see in the experiment, in a higher speed is trimmed about like 4 degrees. So that's the previous one is like a towing tank style of simulation. What we can also do is a self-propelled planning hull. And here is an example. So this is what we do for a self-propelled model. Basically, we will model a propeller in this case. So you can see at the very beginning, there is some disturbance at the free surface. Then the planning hull starts the displacement and the pouring. So you see the trim angle going up a lot. And you know what? This is actually a hull which our client has built and bring it to sea trial. And after we give this result, he told us, yes, you know what? In about 2 seconds, I cannot see the horizontal because it's trimmed too much. And we do see that in our simulation. Basically, the acceleration period is well simulated, and the boat motion is accurately captured. And to give you more example, here is a more detailed zoom-in view about at the stern area. As you see, we simulated the appendage as well, and you see the detailed fluid feature has been captured, and you see how fast the water is cleared from the stern and how it goes around these appendages. So the next one is we are going to talk about is porpoising, because you know the porpoising is a big problem for planning hull. Sometimes it's just really annoying. And for this one, as you see, we have two almost identical hull here. Basically, they have same hull shape, they have same displacement, they have the same design waterline, but there is one difference here, is we have different center of gravity. For the upper one, we have the center of gravity properly placed around the center of the hull. So for the lower one, we just put it a little bit backward. So let's see what happened. So when it's starting accelerate, we see for the properly placed the center of gravity, we see the hull just going up and heave at the constant height and pitch almost at a constant angle, so it's run as expected. But with the one whose center of gravity is not that well placed, you see it's jump up a lot and start porpoising. And there's no way for this kind of hull to stabilize itself anymore. So as we say, so with our simulation, you can identify the L design flaw. For example, the center of gravity is a bit off, so you can avoid this kind of cost design and avoid to changing it after you build it. So that's really how you can use this kind of simulation tool to help you in the design period. So this is about planning hull. Just like Larry said, not only the monohull, we are also doing different kinds of multi-hull. For example, this one, the Catamaran, which is a high-speed multi-hull. For the multi-hull problem, people are always interested in how far we should put this hull in separation. Like, should we put it close or should we put it far away from each other? Here is some examples we have done for the comparison. Basically, in Italy, someone did an experiment with a different separation to see how it affects the resistance, the sinkage, and the trim. And we did a similar simulation. And as I want to mention here, the solid line is from our CFD results, and the markers are from experimental results. As you see, with the different separations, here basically 3 color means 3 separations, we see they have pretty different resistance profile. And our CFD tool have successfully captured it and has a really close agreement with the experiment. So basically, you can use our tools as a design tool to help you to define which is the best separation you want to have for your hull. And with our VOF method, here we're using the HRIC, which is a high resolution interface capture algorithm. And with this algorithm, we can successfully capture all the detailed features about the waves. And we see how the waves interact with each other in the inner region and you see how different they are with the two different separations. So that's for the catamaran. And also, we are doing also the sailboats. So you might wonder what's the difference between the sailboats and all the previous hull. Actually, for the sailboats, because it has a sail, so in the real life, when you are doing you are running different speed, it will have different center of gravity. And more for this particular sailboat, what we are doing is a blind test in a workshop. And here is how we get our simulation results compared with experimental results. You see they agree very well with each other, and I want to remind you again, it's a blind test. So another example of the sailboat. Later, and here is how the free surface looks like. You see it's very clear with our high-resolution interface capture algorithm. Next, let's turn to the big boat. Here is a very famous displacement hull, the DTMV 5415 hull. And again, we have a very good interface capture algorithm. You see how clear the waves looks like. And also, we compare the resistance, sinkage, and the trim in a large speed range. And we see they agree very well with each other. And also, we see how the wave shape on the hull, and also we compare that with experiment, and we see we capture the wave shape very well on the hull. Another thing I want to show you for our VOF method is how we can capture the waves. Here is a wave cut comparison at different locations around the ship. As you see, we have really good comparison with experiment on the wave shape. Basically, we can capture it very well. Also, there's another displacement hull, which is very famous, the KCS container ship. As you see, we also get a very good resistance, sinkage, and trim for this kind of big ship, big hull. And here is how the wave shape looks like, and we have excellent agreement with the experiment. So, as a quick summary, as you see, we have benchmarked various types of hull forms: the displacement, planning hull, catamaran, multi-hull, and the sailboats. And as I have shown you, excellent agreement with experimental results has been found for all of those. Moreover, we are doing more and more public and custom hull design and doing all these different benchmarks. We want to use to improve our solver and also our default setting, so that even though you are not that professional in the CFD analysis, we still want to have your backup with the confidence that you can get a really good simulation results from our software. And I think that's quick summary for my part. I will hand back to you, Larry.
Thank you very much, Chen-Jay, for that presentation. And I should add that in addition to the benchmarks that they've run over at Simerics, we here at Orca3D have been running our own benchmarks as well, and have been seeing excellent results in terms of comparisons with model tests or even full-scale data as well. So, we're gaining a lot of confidence in the capabilities of this Orca3D Marine CFD. So now I think it's time to move on to the live demonstration of the software, just to show you how easy it really is to set up and run a simulation with this tool that we created. So for the live demonstration, we're going to use a 32-foot planing hull known as the Eastport 32. This is actually a hull that is in service and is built here in Maryland. So I'm going to switch over to Rhino now and open up my Eastport 32 model. It's an appended model, so it has not only the interesting feature of having tunnels in it, but you can see this model has shafts and struts and rudders as well. And part of the reason why I'm using the appended model is to show you later how easy it is to add propulsors to your simulation. Okay, so we're ready to start the Orca3D Marine simulation tool, and the geometry requirement for the model that you're going to analyze is that it consists of a closed polysurface or closed mesh. So you can see when I select this surface model over in the right-hand side in the Rhino properties, this one is a closed polysurface. So this is a single closed polysurface. So I'm going to go ahead and start the Orca3D Marine CFD analysis command, select this closed polysurface, and I get the Orca3D Marine CFD dialog where I specify all my input to the analysis. The first set of information that we want to specify has to do with computing the static equilibrium condition, which is, those of you who've used Orca know is a capability that is already built into Orca3D, and also calculating the mass properties. So there's two options for calculating the equilibrium condition and mass properties. I can either specify my weight and center of gravity location if I happen to know that information, say from a weight estimate, or I can specify a flotation plane, and Orca3D will calculate the displacement and center of gravity for you. I'm going to start in this example and specify a displacement. This vessel weighs about 10,000 pounds. Its LCG is about 17.8 feet from the origin. Transversely, it's on center line, and the vertical center of gravity is about 3.35 feet. And I'm going to click the float button, and Orca3D goes and computes the equilibrium. It pre-floats the vessel and comes back with the sinkage, trim, and heel that it calculated for that condition, as well as all the floated ship properties that are necessary for transferring data into Simerics. You'll notice we also computed inertias using rules of thumb in this case. So the inertias were computed by assuming non-dimensional relationships between the gyradii and length or beam. Down here in the Simerics Analysis tab is where you enter the information that's unique to the Simerics tool. First is a project name, which defaults to the name of your file, and that's fine. That's what's going to call my Simerics project file names. Next is the path where you want your project files to be generated, and I'm going to leave that as my default location, and that's fine. Now you need to decide a meshing template. There's two choices, planing or displacement. And of course, this is a planing hull. What you're really doing here is you're telling Simerics in its automatic meshing process how it wants to create that mesh, because it does it differently for a planing hull and a displacement hull. Next, we decide what type of analysis we're going to perform, a resistance or a powering analysis. For right now, I'm just going to do a resistance analysis, effectively simulating a towed model in a model basin. What simulation speeds do you want to analyze? And you can type multiple speeds here, so I'm going to type 20, 25, and 30 knots. And here's where you can specify your properties of your fluid, your mass density, and your kinematic viscosity. The density is actually specified in another portion of the Orca3D interface because it's used for other analyses. The kinematic viscosity can be specified here. And then the next step before running the simulation is attributing the faces. So by default, all of my faces in my hull are red, meaning they're all considered hull faces. But I'm going to attribute the deck face and the transom faces separately. And this gives, again, the Simerics volume measure additional information on knowing how to best create the CFD mesh over in Simerics. So really, that's all there is to it. The next thing I'm going to do is click Run Simulation. And what that's going to do is generate the Simerics files. And you can see in my list of files it created the three speeds, 20, 25, and 30 knots. I'm just going to pick one, say 25 knots, and launch it. And what that's going to do is start up the Simerics user interface. And you can see the progress status bar moving. What that's doing is it's creating the automated volume mesh from the surface mesh geometry that I created over in Orca3D and Rhino. So once that meshing process, which is quite quick actually, finishes, you'll see the entire set of information that was transferred over from Orca. So looking here, you can see I've got a entire domain translated over into geometric entities. I have my deck surface, my hull surface, and my transom surfaces, along with a free surface that was created on the fly to allow you to monitor things like free surface elevation as you're running your simulation. If I go over to my model tab and select the marine item in the tree, you can see that we've also got all of the information. It's a planing hull. I'm doing a resistance analysis. My propulsion options, so my target velocity in meters per second, it's 25 knots in meters per second. There's a ram pump time set up for you. My forward and up directions were based off of the orientations of the model that I had set in Orca. It's got my center of gravity location and waterline position and my fluid properties all transferred over. So really, there's nothing more you need to do here other than go over to the simulation tab and click start, and your simulation will start running. Okay? So very simple process, very easy to get up and going. Let's take a look at the simulation that Bruce started at the very beginning of this, which has been running now for maybe 30 minutes, and see where things are in that simulation. Okay, so this is the simulation we started for a slightly different planing hull, a LAD 42-foot design. And you can see in the process of 30 minutes, it's actually made quite a bit of progress. You started to generate the bow wave over here. So you can see the bow wave forming. You can see the hole in the water behind the transom. You can look at the flow from any aspect or vantage point. So you can look at the flow from the transom view. And let's take a look at how big this model was. If I come over here to my mesh tab and select grid and geometry information, I can see the size in terms of the number of cells in my mesh. This was just under 1.5 million, 1.43 million cells. So it actually has run very quickly to get this far just in 30 minutes. Okay. One of the nice things about the Simerics interface is that it allows you to interact with it while the simulation is running. So, for example, say I want to monitor the heave and pitch of the model while the simulation is running. I'm going to click on this button here to create a 2D plot, which you can see down at the bottom of my screen. And I'm going to plot heave and pitch. Okay. And since we were working in feet, you may find that, well, it's a little confusing to look at heave in meters, so it's very simple to come over here and change the units, display units in feet. So Simerics can work in any unit system you want, and you can see with the red and blue lines how my vessel heave and pitch are varying during the simulation. You can see that I'm 0.36 seconds into the simulation, and I believe that's about 36 time steps. So we made quite a bit of progress in just the 30 minutes. Okay. Obviously, heave and pitch are still varying, so we have not reached a steady state solution, which is really what we're looking for ultimately in our results. Okay. The other thing I might add about the 2D plots is, how do I get this information from a plot into something I can use? There's an option right here to copy plot data into your into a spreadsheet. Okay, so basically it'll cut and paste this information into a clipboard, which you can then paste into a spreadsheet and do whatever you'd like to do with that information. Okay. There's a lot of different things we can show you on this model. I have another graphics view set up over here that's showing dynamic pressure on the hull. In this case, the range of the dynamic pressure might be a little too tight, so I'm going to go ahead and change the range so you can change the ranges of your plots. And again, you can do this all while the simulation is running. Okay. All right, so I'm going to go ahead and stop the simulation for a moment. And what I'm going to do is show you another feature of Simerics, is that you can read in results from a prior run. Okay, so I'm going to click this Load Results button, and I'm going to go over to a run I had done earlier and read in those results. And you'll see that this is a useful way of being able to stop a simulation and restart it at a later date, or if you decide a simulation hasn't run to completion, you can continue your simulation. You can see it's set up as a continuation run right now. Okay, and you can see now it's showing my plot and heave and pitch, and those are reaching a much more constant or steady state values. Okay, so I'm still looking at heave and pitch, but they're leveling out, and that's one indication that my solution is starting to reach convergence. Other types of plots you might create are resistance and effective power. So I'm going to go ahead and add a plot of total resistance and effective power here. And again, you're looking for them to reach a more or less steady state value to decide that your solution has reached a convergent time. We try to give you a reasonable estimate in the setup parameters of your analysis for your simulation time, but you're free to change that to whatever value you think makes the most sense. This simulation to run to completion took us 4 hours. Obviously, we don't have time to do that in the context of this webinar, but it just shows you how efficient and robust the CFD solver built into Simerics MP is. Another thing you can look at are streamlines. So I'm going to go ahead and turn on streamlines for this model. Okay, and for the streamlines, I'm going to choose to plot something. I'm going to plot the magnitude of velocity, and that allows you to see what the streamline flow looks like. Let me make the plot window a little smaller here in way of your model. So you can see the flow in the cockpit region, the recirculated flow behind the transom. So all of that is easy to define and is available as a natural part of the Orca3D Marine CFD system. Next thing that I want to show you is animations. You notice over here there's a section that talks about result saving frequency. That says how many time steps between saving the full set of CFD results. And not only does that let you come back to a prior run at a particular time step, like I showed you when I loaded results, but it also lets you create an animation. What it does is you come over and select, I'm going to save an animation, and you'll see all the results files that have been saved. In this case, it would have been in increments of 5, and you pick the view that you want to create the animation for, and it will automatically generate an animation file that shows you that view with whatever information you're currently displaying for that simulation. So here I have a couple of animations already created that I wanted to show you. So for example, a catamaran in an overhead view. Okay, so you can see the wave patterns coming from the catamaran. The Eastport 32 looking in profile view. And again, here I've turned on pre-surface elevation and dynamic pressure on the hull. You can see the original hull in its original static location, so you can get an idea of the heave and pitch. A port bow view of the same run. And a workboat analysis with waves and streamlines turned on. Okay, so there's quite a bit of flexibility here, and really it just depends on what you set that saving frequency to define how many frames you'll have in your animations. Okay, so now I'm going to go back to Rhino for a moment, to the same example we were looking at before for the Eastport 32. And I'm just going to show you a couple of additional features that I think are of interest to people. The first is defining propulsors. Remember I said if I choose a powering run, I'm going to have the opportunity to define my propulsors. And sure enough, when I select that, you get a propulsors tab, and you can choose to add one or more propulsors. The definition of a propulsor consists of defining its rotation, its diameter, so these are about 1.5 foot diameter propellers, its hub diameter, its thickness, and then its location. You can specify its location here in the input fields, or you can, of course, use Rhino's interactive capability to locate your propulsor. So I'm going to first move my propulsor and snap to a point on the shaft so that I can set my propulsor direction to match the shaft direction. Okay, and then I'm going to move it again and move it to the center of the shaft line. Okay, so that's how simple it is to define your propulsor location in your model. The last piece of information you have to define is its performance. And in Simerics, we use a Huff and Ordway actuator disc to model the propulsor effects, both in terms of the thrust, torque, tangential flow velocities. So we need to provide information about the propeller in terms of its open water performance. There's three ways you can do that. You can choose a B-series propeller, specify your own custom open water curves, or just specify a constant thrust and torque. I'm going to choose the B-series propeller, and this is a four-bladed prop with an expanded area ratio of about 0.75 and a pitch to diameter ratio of about 1.3. The other part is, what do you want the operating profile to be of your propeller? And I'm just going to say it's a fixed RPM at 800 RPM. So basically, that's all there is to adding a propeller. Nothing else needs to be done. All the other input is the same. You just click Run Simulation, and it'll generate the same simulation we saw before, but now with the propulsor added to the problem. Two other issues I wanted to address very quickly has to do with multi-hulls. So some people might ask, how would you run a catamaran? I'm going to open up a catamaran model here and run the same Orca3D Marine CFD analysis tool. And the only difference is that when it asks you to select the closed poly surface or mesh to analyze, you just select both of them. Okay, it'll treat them as a rigidly connected body. All the other input is identical to what you had before. One thing to notice in the dialog here is that it's already preset with values that I had entered previously. So that is, we persist, of course, all of this information, your weights, flotation plane, project name, face attribution, all this information gets persisted so that if you want to make a change later, you can do so. So very simple to do a multi-hull, nothing really any different than a monohull. And the only other item I wanted to emphasize was an asymmetric run. Here I have a model that displays asymmetry. It's a sailboat hull, but it's yawed and heeled 5 degrees. What would I do differently in the analysis there? The only thing you would do differently there is you would check this box down here at the bottom that says solve the full asymmetric problem. So when Simerics does its meshing, it knows, oh, this isn't a symmetric problem. I need to generate the full domain, both sides. Obviously, there'll be twice as many cells as you would have in a symmetric problem, so the problem solving will require some additional time. But there's nothing, of course, you can do about that if you have an asymmetric problem that you're trying to solve. Okay. So hopefully, this wraps up the live portion of the demonstration. Hopefully, I've been able to show you how straightforward and easy it really is to set up and run a CFD simulation with Orca3D Marine CFD. In a moment, I'm going to pass the control back over to Bruce to talk about the licensing options for Orca Marine CFD. And then if we have some time after that, we'll go back and answer some questions that may have been posed. So Bruce, next slide is up to you.
Okay, thanks, Larry. So for the pricing, there are two parts to this. The first is Orca3D, and you need Orca3D level 2 to run the CFD tool. So if you don't have Orca3D, the plug-in for Rhino. Orca3D Level 2 is $2,780. And if you do have Orca3D but you have Level 1, you can upgrade that to Level 2 for $1,390. Then on the Simerics side, we have two options to offer here. The first is for an office which is using CFD on a continuous basis, and those are essentially leased licenses. So you can have a 3-month license for $3,375 or a 12-month license for $10,000. Then the next option would be appropriate for an office which is only using CFD occasionally, say on a project-by-project basis. And that allows you to pre-purchase either 3 months or 6 months of 1-month licenses. So, for example, the first one, 3 months of usage during a 12-month period, you can turn on the license for 3 1-month periods anytime during that year. So if you needed it in January and June and October, because that's when you had projects in-house, that's what you could do. And similarly for the 6 months of usage during the 24-month period. In our follow-up email to the webinar, we'll include a summary of this pricing information, as well as links to download the version of Orca that has the CFD tool in it, and as well to download the Simerics MP. If you don't have Orca now, it will run as a 15-day evaluation license, and Simerics will run as a 30-day evaluation license. And that'll give you time to see how easy it is to use and to do some benchmarking on your own. The email will also include a link to a short tutorial video, and you'll find instructions on how to go through the whole process. It's basically what you saw Larry do today in the Orca3D help file. So we do have time for some questions. The first question is, how much CFD experience do I need? And what we're trying to do here is, as Rich said earlier, is to create a tool where you don't need to be a CFD specialist to use this. You don't necessarily need CFD experience to use it, but of course you should have a naval architecture background. But if you do have CFD experience, I think you'll appreciate the ease with which you can set up and run a simulation with this tool. We had one question regarding, a couple of questions actually, trim tabs, interceptors, and lifting foils. And yes, you can model and simulate all of those. With very good results. So yes, you can model those sorts of appendages. We also had a couple of questions about hardware. So Larry is running on a laptop, a Dell Precision 6800, about 3 years old, at a 3 gigahertz i7 processor with 4 cores. And the CFD tool will make use of all the resources that are available on it. From a practical point of view, I've found that I'm able to continue to do things like email and spreadsheets and so forth while that's going on. In terms of a hardware recommendation, any modern computer will run it. Obviously, the faster the better. The memory requirements are pretty reasonable. I think if you had 16 gigabytes, for example, you'd be fine. Larry, there was a question about rendering the CFD mesh, whether that can be shown.
Right. So yes, there is an option to turn on the grid. So of course it's a 3-dimensional grid, and you're looking at it on 2-dimensional surfaces. But you can view the grid on the hull, of course, on the free surface. Anywhere that you have a surface defined in your model, you can view the 3-dimensional grid that's created. If you look at the grid, say from a top view, you can see, without getting into too much detail, There's a refinement zones of the grid that are around the hull and in way of the free surface. And as you get further away from the hull boundaries, the grid gets coarser. So there's plenty of visualization capabilities of the grid, and in addition, there's also the ability to change the grid once you're in Simerics. Our goal is to not have you need to do that in general, but of course there's always going to be special cases in certain geometries that do require changes from the default grid, and you can perform all of there's a full control of the meshing capabilities within Simerics NP, so you can create local refinement zones and things like that if you need to.
And we had a question about refining the meshes to see about the CFD solution converging, and while, as Larry has described, the intent here is to automate the process of meshing as much as possible. But of course, you have control over the Rhino mesh on the Rhino side with the standard Rhino meshing tools to make adjustments there, and then that's used to create the CFD mesh on the Simerics side automatically. But you also have control there to refine the mesh if you'd like to do a mesh sensitivity study. There's a question about the model requirements. And as Larry said, your model needs to be a closed poly surface or a mesh. So in Rhino terms, that means you cannot have any naked edges. So you can use the show edges command in Rhino, which will highlight any naked edges that you have and we'll need to go back and fix. You should also consider whether you should simplify or de-feature your model. So we showed an example with the superstructure there, which is nice to see the airflow around the superstructure. But of course, that increases the size of the CFD mesh in terms of cells and slows things down. So if you're not interested in that particular aspect of the analysis, you can do something like the model that you see here, where there's just a simple flat deck. In terms of the hydrodynamics, it will have very little effect, but it will increase the speed of the solution. There's another question about units. So of course in Rhino, you can set the length units. In Orca, you can set all of the other units, speed, power, weight, and so forth in the Orca properties. When the files get transferred over to Simerics, they're all in SI units. And in Simerics, you can adjust units as you see fit as well for things like, if you want to see the heave in inches rather than in meters, or speed in kilowatts rather than horsepower, you can make those changes over there. Let's see if we have some more here. We had a question about tunnels and appendages, and so of course Larry showed one example, the Eastport 32 with tunnels and running gear, and so yes, that can be modeled and simulated. So I think that's all we have time for. This is probably a good point to wrap things up. We have a couple more questions which we will address in a follow-up email to everyone, as I said, which will also have the links. If you have additional questions that you think of after the webinar, please send them to support@orca3d.com. So again, thank you for joining us, and we look forward to helping you make CFD an affordable and a practical part of your tool set.